Swayam Prabha. Digital India. Educated India.
Welcome back to the course Mechanics of Solids. So, in the last lecture we developed these strain components, right. So, all the strain components are 0 except gamma theta z, and that was derived as r into d phi dz, and based on these strain components we can calculate the stress components using the Hooke's law, whatever we have discussed earlier, right. So, using Hooke's law, we can simply write sigma r, sigma theta, sigma z equal to tau r theta equal to tau r z, all are 0, and only remaining stress, that is nothing but tau theta z, that is equal to g, that is the shear modulus multiplied by gamma theta z, which is nothing but g r d phi dz. Okay. So, what we have got at this point, that if you consider a circular shaft under constant twisting moment mt, okay, and if you consider the small deformation situation, then you will be ending up with only one stress component, that is tau theta z, that is the shear stress happening on the cross section, okay. That is the shear stress happening on the cross section, and based on this equation you can say shear stress is minimum, that is 0 at the center of the circular shaft, and that is becoming maximum at the periphery, okay, fine. So, now let us come back to this figure. Now, we will be talking about the equilibrium requirements, okay. We will be talking about equilibrium requirements. So, what is your equilibrium requirements? Because you are applying the twisting moment, and that twisting moment is causing the development of this shear stress, right. So, this shear stress is nothing but the internal say adjustment, this internal the force, shear force, which is developed at each cross section, that will try to balance the externally applied twisting moment mt, right. So, that we are getting from this figure. So, here actually what you are getting? You are getting tau theta z acting on the plane. So, this is the say cross sectional plane. So, therefore, to balance, as you know, so cross shear will be always equal. So, therefore, you will be having the shear stress like that. Now, the same thing we are just showing in this particular segment, say. So, this is the variation of tau theta z, this is minimum at the center and maximum at the periphery. Okay. Now, we are considering a small area, say delta A, on the cross section. Okay. So, on that small area delta A, your tau theta z is acting, right. So, therefore, the shear force developed on that area is nothing but tau theta z into delta A, that is the shear force acting on that small element delta A area. Okay. So, this shaded area is nothing but delta A. So, therefore, the shear force is nothing but tau theta z into delta A. Now, if you integrate over the whole area, okay, that will try to balance the applied twisting moment, agreed or not. That is very simple, right. This shear stress is getting developed due to the application of the external moment mt. So, if you do the integration over the whole area, then whatever shear force you will be getting, that will try to balance the externally applied twisting moment mt. Okay. So, then the equilibrium requirements is nothing but, considering the equilibrium, we can simply write over the whole area A r, okay, into tau theta z dA is equal to mt. Agreed? So, tau theta z into dA is the shear force acting on the small area delta A, right, and if you multiply that with r, so that will give me the twisting moment, okay, caused by that shear force, and if you integrate over the whole area, whatever twisting moment you will be getting, that should be equal to the externally applied twisting moment mt, okay, fine. So, this is your equilibrium requirement, and coming from the equilibrium condition or satisfying the equilibrium condition, you can develop or you can satisfy or you can get this equation, okay, fine. Now, we are going to develop the stress and deformation relation, stress and deformation in a twisted circular shaft. So, this I am calling as say equation 1, okay. So, please stick to the equation number, we will be referring this equation number subsequently, okay. So, you have got from equation 1 we have got mt is integration over the whole area r into tau theta z dA, okay. This can be further written as integration over the whole area r, instead of tau theta z I can simply write g r. So, that is the relation already we have established d phi dz into dA, okay, fine. That can be further written as, because g is constant, this is constant, this is also constant because rate of twist or the twist per unit length, okay, that is also constant. So, therefore, we can simply write mt equal to g d phi dz r square dA, integration over the whole area, okay. So, or we can write mt equal to g into d phi dz. Now, please tell me, because this is from your earlier knowledge, right, what is this? Integration over the whole area r square dA, this is nothing but the polar moment of inertia. If you go back to your physics class or earlier mechanics class or whatever you have gone through. So, if you look back, so this expression is nothing but the expression for polar moment of inertia. So, therefore, I can simply write I z, because with respect to z axis you are considering the moment of inertia, and that I am calling as equation 2. So, I z we know that is integration r square dA, and that is your polar moment of inertia. Now, since we are considering the circular shaft, okay, so we know that for a shaft of radius r naught and diameter say d, your I z is simply equal to your I z equal to pi r naught to the power 4 by 2, or in terms of diameter pi d 4, it is 4 by 32. Okay. So, this you can calculate or you can determine by using the basic principle. Okay. I am just giving you the expression for polar moment of inertia for the circular shaft. Okay. Now, from equation 2 I can simply write d phi dz from equation 2. Okay. I can simply write d phi dz is equal to mt by g I z, okay, which can be further written as d phi is equal to mt by g I z dz, okay, which can be integrated over this limits, which can be integrated over this limit say 0 to phi d phi equal to 0 to L mt g I z dz. Now, what it gives me? So, it gives me say phi equal to mt L g I z. Now, here if you look at, if I consider say I am considering the length of the slender member is say L in the z direction, okay. The length of the slender member is L. Now, if I consider the twist, I mean relative, that is a relative twist, right. So, bottom I mean say plane, bottommost plane is experiencing say 0 twist and the topmost plane is experiencing say twist of phi. Then this d phi is basically getting the range from 0 to phi and that is ranging from 0, that means at the bottom plane to the top plane, that is L. So, what I am getting from this expression? So, this expression I am saying say equation 3. Now, what I am getting from this? I am getting the angle of twist, okay, between two ends, that means the bottom end and the top end, right, between two ends is given by this. So, if you want to find out how much twist is happening in that slender member due to the application of this twisting moment mt, then this is the expression, okay. This is the expression for finding out the twist. Now, from this it is very much clear that as you increase your L, that is the length of the slender member, your twist will be more, is not it? As you increase the length of the slender member, your twist will be more with the same amount of twisting moment mt, okay. Now, again we are just going back to this expression tau theta z, already we have seen g r d phi dz, okay. So, from this I can write tau theta z equal to g r, instead of d phi dz I am writing this mt g I z, okay, fine. So, that gives me mt r by I z. So, what I am getting? I am getting the shear stress developed due to the application of mt in terms of the geometrical parameters. Now, if you look at, as you go towards the, because that is obviously true, because as for a constant amount of twisting moment, as you go towards the periphery you will be experiencing maximum shear stress, that is already known. Now, if you know how much twisting moment you are applying, if you know where exactly you are going to find out the shear stress at the periphery or in between or at the same, I mean at the center it will be 0, because r is 0 means that is 0. So, if you know the magnitude of or the value of say radius r, where exactly you want to find out the shear stress, and if you know the polar moment of inertia of the circular shaft, you can find out how much shear stress is getting developed at that particular location. Okay, fine. So, now from equation 3 we can again write from equation 3 we can write mt by phi, okay, is equal to Giz by L. That is also very important relation, where mt by phi, it is very much similar to your say spring constant. If you recall, what is that? The moment or the twisting moment required per unit twist, right. It is very much similar to if you try to draw or try to map with, I mean try to map this with your say spring constant. Spring, what was the definition of spring constant? Force required for per unit displacement, right. Similarly, this is the twisting moment or the moment required for per unit of twist. So, this mt by phi is the twisting moment per radian of twist and is called as torsional stiffness. Like your spring constant, that is a part of torsional stiffness. Okay. So, now one thing is very clear from this discussion, that if you deal with a particular material, then G is constant. If you deal with steel shaft or aluminum shaft or say copper shaft, your G is constant because G is the material property. Okay. And if you are dealing with a particular length of the shaft, then L is also constant, right. Then basically your torsional stiffness will be dependent directly on your polar moment of inertia Iz. If you increase the polar moment of inertia, your torsional stiffness also will increase. Okay? Fine. So, now we will look at the torsion in hollow circular shaft. Torsion of hollow circular shaft. Okay. So, please come back to this figure. So, this is one hollow circular shaft where Ri is the inner radius, Ro is the outer radius. Okay. This is the variation of say shear stress tau theta z. Okay. It is under the action of externally applied twisting moment mt. Okay. Now, for this hollow circular shaft, your Iz is simply equal to, as we have calculated, 2 minus pi Ri to the power 4 divided by 2, right. That gives me 1 minus Ri to the power 4 Ro to the power 4. Okay. Now, what you are getting from this actually? So, your polar moment of inertia for a hollow circular shaft is given by this expression, fine. Now, if you look at this term, this term is basically giving me the fourth power of Ri by R naught radius, I mean ratio, right. Fourth power of Ri by R naught ratio. Now, basically as I told you that, I mean if your G and L is, I mean they are constant, then your torsional stiffness is completely dependent on the polar moment of inertia. Now, if you look at this expression, if you apply say solid circular shaft, then I z will be simply for solid. Now, for hollow, this I mean this polar moment of inertia is taking the expression like this. Now, this part is very negligible, is not it? R I by R naught to the power 4, that ratio with the fourth power. So, that is very negligible. So, this basically this hollow, if you consider the hollow circular shaft, okay, then basically your polar moment of inertia is not getting affected much, that I mean to say. Your actual polar moment of inertia for the solid circular shaft is this, but when you are considering the hollow shaft, then your polar moment of inertia is this much. So, this is the part which is getting multiplied with this factor. So, this factor is almost equal to 1, because this ratio is taking to the fourth power. So, if you consider hollow circular shaft, your polar moment of inertia is not getting much affected. So, if your G, that is the shear modulus, if you are dealing with same material, say you are having one solid circular shaft with say steel, made of steel, and one hollow circular shaft again made of steel, then your G is same for both the shafts. And if you are considering the same length of the shaft, then L is also same for both the shaft. Now, after doing this analysis, basically you are also saying, or you are also getting the idea that your polar moment of inertia is not getting affected much, right. So, always your idea should be that you use higher torsional stiffness, right. For any material, any kind of shaft, if you get higher torsional stiffness, that will be always better, right. But that you are not getting properly from this, because IZZ for both the cases are almost comparable. So, you are not getting much enhancement in the torsional stiffness if you use a hollow circular shaft. Then what is the advantage of using hollow circular shaft? Now, advantage is that you are getting almost same amount of polar moment of inertia, and if you are using the same material like G, IZ, L all are say same, then basically you are getting the same amount of torsional stiffness. So, whether you are using the solid circular shaft or the hollow circular shaft, you are getting the almost same amount of torsional stiffness, but at the same time you are getting reduction, significant reduction in the weight of the shaft, because you are taking the inner part or the inner material of the solid circular shaft out, right. So, therefore, this hollow circular shaft is giving you the almost comparable or the same amount of torsional stiffness at lower amount of weight. So, therefore, when in different mechanical system or maybe some other say mechanical say machines where the weight is an issue, because the shaft will be carried by the bearing and all those things, right. When the weight is an issue, then in that situation you will be using the hollow circular shaft, because your torsional stiffness will be remaining almost say comparable. Okay. So, with this I will stop here today. So, in the next lecture we will be continuing with the same discussion and we will be solving couple of numerical problems. Thank you very much.